أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله والصلاة والسلام على رسول الله. This is the final tutorial for the year, and this is basically a quick one on the Faraday's law on the induced current, and I'm just going to go very quickly on the induced current idea, which comes from the fact, as we saw in class, the fact that when you move when you move a magnet, for example, into the coil, so the magnetic field, this is my coil, the area, and as you move it closer, the magnetic field is stronger, and if the magnetic field is stronger, then you see there is an induced EMF, which is shown by the deflection. So once you move it where you change the flux, then you get an induced EMF. In this case, it's positive. It's increase in the if it is fixed, if you do not move it, if you do not move your hand, then you see no deflection and there is no induced current. If you move it on the other way, or the other side, so what does that mean? That means the magnetic field is getting less. So if the magnetic field is getting less, that means the induced EMF is negative on the other side. And the induced EMF is defined by this formula here. The induced EMF is defined by this formula right here, which is simply the negative rate of change of the flux. So this is really related to motion. So the induced EMF is related to the motion of the magnetic field, or the change in the rate change of the magnetic flux. Okay, so as you move this away, then you change it. You have a change in the flux with respect to time, and then from there you get an induced EMF, which is basically measured in volts. Okay, so Faraday's law says that the induced EMF in a coil is proportional to the negative rate change of the magnetic flux. Okay, so this is what we have here. This is what the induced EMF is. Remember, if you have induced EMF voltage, this will give you an induced current. Now, if we look at this here, now this can be positive, okay, and can be negative, and can be equal to zero. If the rate change of the flux is positive, that means the induced EMF, positive multiplied by negative, is negative. That means the induced EMF, the induced EMF, if this is the induced EMF, is less than zero. Okay, and if this is negative, okay, then negative multiplied by negative, positive, so the induced EMF is greater than zero. And if it is equal to zero, of course, the induced EMF is zero. Now, what we refer to in class is Lenz's law, and Lenz's law is defines or determines for us the direction of the current, the induced current. Now, let's look at this one here. If phi is positive, that means the area normal hat, the normal, which is n hat, is perpendicular to, or it's along the same direction as the magnetic field. So that's positive. And if d phi dt is positive, right, that means the induced EMF is negative. That means the current is negative. Negative means it's counterclockwise, so it's in this direction here. That's counterclockwise. However, if d phi dt is negative, negative multiplied by negative is positive. That means the induced EMF is positive. That means the current is positive, and this means the current is clockwise. Okay, and obviously the other, if this is d phi, then everything is reversed. Okay, so now let's take an example. If we take this example here, where I have, and this is the example that I want you to concentrate on. It's a very important example, which was not explained very well in the class. So suppose that I have magnetic field, uniform magnetic field, and it's into the page. So into the page, the magnetic field, which is minus k hat, some number b0 multiplied by k hat, okay, or along the direction of k hat. Now, if I apply an external force, so this is an external force, in such a way that I pull this rod here along the frictionless, so there is no friction here, and I pull it this way. As I pull it this way, this area increases, so the area is increased now, and the distance here is L. Okay, the distance here is L. So what does that mean? What does he want? He wants, first of all, he wants you to find the induced EMF. Now, if the external force is applied to the conductor so that it moves to the right, this is the conductor here, moves to the right with some velocity v along the I hat direction. Okay, so this is an external force that I apply in such a way that I produce a constant force. Constant force means what? Means my external force must be equal to the magnetic field force that it's already there, because remember, I have a B, I have a V, there are charges moving across here, and that means I'm going to produce an F. Okay, so the first thing that I wanted to calculate the magnetic flux. The magnetic flux, remember, if I want to find the induced EMF, I want to find d phi dt, and the first thing that I need to do is phi. Phi is BA cosine theta, which is BA, because this is into the page, right, the magnetic field, and the area is perpendicular to it, it's parallel to it, so that means the angle is 0, so that means cosine 0 is 1, then I have BA, and the area is simply x multiplied by L, that's the area, so my phi is simply BLX. The induced EMF will be simply as defined by previously, it's simply d phi dt, which is dt of this number here, or this value here, and both B is constant, L is constant, so they come out, and the only one that is varying is x, because this is moving along this way. Okay, so that means I have dx dt. Now, what I wanted to know, is this greater than 0 or less than 0? Now, dx dt, remember, this is moving this way. If it is moving this way, that means it's greater than 0, because x is continuously increasing. Dx dt is continuously increasing, or positive. Okay, x is continuously increasing, so dx dt is positive. If this is positive, positive multiplied by negative is negative, so the induced EMF is negative. Okay, if my induced EMF is negative and my phi is positive, so my phi is positive, and my induced EMF is negative, what does that mean if I go back to this? So this is positive and negative, that means my induced current is negative. Negative means counterclockwise, so that means my induced current, which is simply the induced EMF divided by the resistance, and the resistance is this guy over here, right? Then that's my induced current, and because it's negative, the direction is counterclockwise. Counterclockwise means what? It means along the rod, it's this way. Okay, so this way is J hat. Right? That's counterclockwise, right? Okay, so if it is J hat, then the magnetic force, which I can calculate easily, so L is this, and it's along J hat, right? And cross B, which is along the negative K hat. So J hat was 0, 1, 0, 0, 1, and then 0, 0, minus 1, 0, 0. So that means the only one that is going to survive is this one, the I hat. So I have minus negative I hat, and which I have here, negative I hat. So this is B, this is ILB, right? So this is B, ILB, and remember what I is, right? If this is I, then if I substitute for I, right, I get B square L square V divided by R. That's what the magnetic force is. Now, because it's moving with constant speed, because the bar, he told me that it's moving with a constant speed, that means the external force is equal to negative this, so they're balanced. So if this is moving this way, that's my FB, and so that means my external force, F external force, is along the I, it's opposite to it, and it's moving in the other way I hat. So it's not moving, but directed the other way. Now, the other thing, I can calculate the power. Remember, power is simply work or energy over time, right? And energy, in this case work, is equal to F multiplied by D, right? And D over T, so this is F D over T. F D over T is simply what? Velocity. And that's why I have power is simply the external force multiplied by the velocity, which I know. The external force is this guy over here, and the velocity is known. So when I do that, just multiply by the velocity, I get all of this squared divided by r. And if you notice that this is simply BLV, which is E squared over r, or I squared r, which we know it from before the power. Okay, so again, what happens now? I want to give you a different scenario. In the previous example, the bar is moving this way. So that means d phi dt is increasing, right? Or it's continuously increasing. What happens if the applied force now is this way? So the applied force, the external force of the applied force is this way. If it is this way and V is this way, what does that mean? That means that, again, if I go to the induced EMF, it's simply d phi dt and then b dA Lx, and then I have dx dt. Now, in this case, x is, if it is moving this way, then x is decreasing. That means what? That means this is negative. This is less than 0. If it is less than 0, if this is less than 0, negative, right? And negative multiplied by negative, I get a plus BLV because dx dt is less than 0. And then I can find I, which is E, the induced EMF. Sorry, they're not consistent here, the symbols, but this is the induced EMF, BLV, right, divided by R. And because it's positive, it is now clockwise, so it's this way. Okay, so the current here is this way, which is minus j hat, which I can work again, find from here FB, which is minus j hat cross k hat. And again, I can do that and find that it's equal to, let me just see. So it's minus j hat, so 0, minus 1, 0, 0, minus 1, and then minus k hat, 0, 0, minus 1, 0, 0. So that, as you can see, the only one that is going to survive is this guy, minus there, which is I positive. So FB, in this case, the magnetic force is ILB, and multiplied by along the direction of I hat. So the external force will be balanced by this, and it will be ILB in the negative I hat direction. And from here I can find the power. P is simply equal to F V. I have F and V is given, so I can from there find the power or find whatever he wants to do. He wants to ask me. So just make sure that you understand that the power can be calculated in two ways. You can just simply say power is equal to I square R, and I is simply the induced EMF over R, and this is BLV divided by R, and I square, so you just square this and then multiply it by R. You get this. Or equivalently, you can say that the work is equal to FD, and D is equal to VT, and you can put that the power, this is the power here, is equal to W over TFV. So power is equal to V over W over T, which is equal to FV, and then F, you have it, and you just multiply by V and you get that, and that's the end of it. So this is something that, as I said, I got a lot of questions on this, and I think it's very clear now and very obvious. Thank you very much, and good luck to all of you.